Okay, so today we're going to point out a problem that you should already know you have. Okay, here's the problem you thought. Okay, so if we want to find moles, we've got two ways right now. We can count how many pieces, and that's not practical. Or we can weigh things and do some math, right? And that works really well unless the stuff you're trying to figure out is a gas. Because if I wanted to figure out how much helium I had in the balloon, I'd weigh the empty balloon and then fill it up full of helium, and then I'd put the balloon back on the scale, and there'd be a problem. It'd float away, right? Gases are hard to weigh. So that's the problem. Gases are hard to weigh, and lots of the compounds we're dealing with are going to be gases. So if they're hard to weigh, what can we do? Okay? If we're not going to be able to weigh them, what can we do about it? What we can measure about them is volume. You can't measure how heavy they are, but you can measure how much space. And if I put in more helium, my balloon's going to be bigger. Okay? And that works great, except there's one minor difficulty, and that is volume is not conserved like mass. Okay? Volume's not conserved, so I need to go from moles to volume, but volume's not conserved. I can squeeze the gas and make it smaller. A hot air balloon works because when you heat the air gets bigger. The same amount of air gets bigger. So its volume changes based on temperature and pressure. So the same amount of gas can take up different volumes at different temperatures and different pressures. One of my favorite tricks is to take, when I go on flying, is once you get past TSA, you buy a bottle of water and drink some of it. Okay? And drink some of it as the plane's going up. And when you get to altitude, close it. Put the lid on it. Then when you go back down, the water bottle will get crushed. Okay? And then if it's a layover, you take that same bottle, still sealed, back up, and you go back in the plane, and it reinflates. It's because the pressure inside the plane is different before and after, at the ground level and at altitude. So that pressure affects how much space the gas takes up. So we don't want to measure at the ground and at the top. We want to measure the same place all the time. So what they have decided is that we're going to compare these gases at the same temperature and pressure. As long as I keep the temperature and pressure the same, then volume should be proportional to moles. If I keep the temperature and pressure the same, volume should be proportional to moles. Twice as much volume, twice as many moles. Which is, if you're in a room, that's usually temperature and pressure stay the same. Right? So they picked a standard. They call it standard temperature and pressure. The reason why they picked the standard is because of Avogadro's hypothesis. We talked about his number. Why did he get a number named after him? He's the one who figured out it's how many particles is the important part. Okay? And here's what he said. At the same temperature and pressure, equal volumes of gas have the same number of particles. So we have to decide a temperature and a pressure. And the temperature and pressure they picked was ones that were easy to recreate. And they had to do this in the 1700s. So what could they easily recreate in the 1700s? Well, they could measure temperature with a thermometer, but thermometers from one place to the other weren't necessarily standardized. So they picked a temperature everybody could make all the time, and that is 0 degrees Celsius. Okay, they picked 0 degrees Celsius because if you have ice water Once you let it stabilize and there's still ice floating around, that means the ice is at its melting point, 0 degrees Celsius. The water is at its freezing point, 0 degrees Celsius. So they picked 0 degrees Celsius because if you got ice water, you got 0 degrees Celsius. Okay? That's why they picked it. It was easy. 1 atmosphere pressure, we're usually about 1 atmosphere pressure. So, right, in this room we're at about 0.97, I think. I remember correctly, but I looked last time. Okay. So, now, there's other units for temperature. Sometimes you'll see it as 237 K. That's 0 degrees Celsius. Sometimes you'll see it as 101.3 kPa, kilopascals. That's 1 atmosphere. We'll talk more about those units when we study gases. So the reason why they picked a standard temperature and pressure, because if I have equal temperature and pressure, equal volumes, equal numbers of gas, twice the volume, twice the amount of gas. Okay? So if you happen to be at standard temperature and pressure, at STP, we're not going to write out standard temperature and pressure all the time. We're going to call it at STP, at standard temperature and pressure. Remember, at STP is describing a room, a cold room. Right? 0 degrees Celsius, you'd want a jacket on. Pretty heavy one. And if you're at STP, 1 mole of gas, somehow sig fig got cut off of this, is 22.42 liters. That's about 11 2-liter bottles. Yeah. Okay. 22.42 liters. So if I had 22.42 liters, that would be 1 mole of gas. Okay. This is called, well, it's the volume of a mole, so they call it the molar volume. Hey, we have a new conversion factor. 1 mole equals 22.42 liters. And we need it because we can't weigh gases. Everybody read that? Okay. Oh, that is not what I clicked on. I know what I clicked on. It was not that. What is the volume of 4.59 moles of CO2 gas at STP? Eventually we'll learn what happens if the room isn't cold. But for right now, we're all going to pretend we work in a really cold room. Well, what unit do I want to get rid of? Moles of CO2. So it's got to go on the bottom. What can I turn moles of CO2 into? Well, I can turn it into grams of CO2. I can turn it into molecules of CO2. And now I can turn it into liters of CO2. And since they're asking for volume, liters is the right choice. And 1 mole is 22.42 liters. Yeah, regardless of the gas, takes up the same amount of space. Because most of it is empty space. I mean, think about what happens to water when you boil it. How much steam you can get out of a little cup of water. So every 18 milliliters makes 22.4 liters of steam. 18 grams is 18 milliliters, right? So that's 1,000 times increase. And all that increase is empty space. So they're mostly empty. Okay. So you push those buttons, 3 sig figs, because the 4.59 has 3 and the 24.2 has 4. And I get 103 liters of CO2. Oh, see, again, I did not click on that. I don't know what it's doing. I click on something very specific, and it doesn't go there. So I wanted, there we go. What's the volume of 8.8 grams of CH4 at STP? We want to get rid of grams of CH4. I want moles of CH4. 1 mole of carbons 12.01 grams. Hydrogens, 4 of them, 1.01 grams, or 4.04 grams. So that adds up to 16.05 grams. Just want to say to lots of people, when you're doing this math over here, you're leaving those grams off. I wrote something about it on your paper when you hand it back today. I do it every time, right? So I'm just asking you to do what I do. Okay? They can be moles, but they don't want moles. They want liters. So I can turn moles of CH4 into other things. Now I want to turn it into liters of CH4. 1 mole is 22.42 liters. Actually, this is the mole to liter was the easiest one because there's only one number and you don't have to do a scientific notation. So 8.8 divided by 16.05 times 22.42 equals 12. And that's liters of CH4. I could have gone to molecules. We can stick this in so we can do any, right? So once I turn into moles, I can turn anything I can turn moles into. So if I got liters, I can turn into moles. Those moles I can turn into grams and particles. If I got particles, I can turn into moles. Those moles I can turn into grams and liters, if it's a gas at STP. But notice what I got here. I've got grams of CH4, and I've got liters of CH4. Huh. What could I find out about CH4? Its density. So 8.8 grams was 12 liters. I divide those, I find the density. But it's actually easier than that. Since the same amount of gas always takes up the same amount of space, I can pick any amount of gas. And I'm going to pick 1 mole. Because to find density, I need mass and volume. Right? I need mass and volume to find density. If I pick 1 mole, I can find mass off the periodic table. I can find volume, 22.42 liters. So that's all I have to do is take the molar mass and put it over the molar volume, and that will tell me the density. Or I could start off with some grams, figure out some liters, and do the division, but I'll get the same answer either way. So, what's the density of CO2 at STP? If I assume 1 mole, then I've got 1 carbon and 2 oxygens. Carbon's 12.01 grams, oxygen 16.00 grams. That's 12.01 grams of carbon 32.00 grams of oxygen gives me 44.01 grams. That's my mass. What's my volume? Well, 44.01 grams is 1 mole, so 22.42 liters is 1 mole. Equals. Four sig figs in both my numbers, so 4 sig figs in my answer, and units of grams over liters because they didn't cancel out. So as long as you know the formula, you know the density. So the reason why helium floats is because helium's molar mass is 2 over 22.42. Really low density. Or sorry, 4 over 22.42. Remember the one that sunk, we sunk the aluminum boat? That was sulfur hexafluoride. So six fluorines, so 6 times 19, which is 6 times 20 minus 6, 112, or 114, plus 32 for the sulfur. That's 144. 144 grams for that gives you a much higher density, right? Right? So sulfur hexafluoride is much more dense than the air around us, which is O2 and N2. Actually, we don't. You don't buy it in the big tanks, and it's expensive, and it's actually a horrible greenhouse gas. It's worse, much worse than either methane or carbon dioxide. So you don't want sulfur hexafluoride running around. Okay? It's a nasty greenhouse gas. Okay, so I want you to fill in this table, do the work someplace else, either on the back or on a separate sheet of paper. So I want to take that 23.8 liters of helium and find the mass. So you can take that liters, change it to moles, moles to grams. And I want to figure out how many representative particles there are. So it will be, change it to moles, moles to representative particles. What kind of particle is He? Well, He is an atom. So you're going to figure out how many atoms there are for He. And then you can find the density of He, either using the mass and the volume or the formula weight and the molar mass.